Hello and welcome to class 6. This is on the electric field, its divergence and curl, and a sample calculation of the electric field using derivatives and differential calculus. And this covers sections 2.1 and 2.2 of the textbook, and we'll get to use the divergence theorem and Stokes theorem, which we learned last week. So how can we find the part of Maxwell's equations is the divergence of the electric field? How can we find the divergence of the electric field? Well, we actually use Gauss's law and the divergence theorem. And just to remind you, the divergence theorem says that the integral over a volume of the divergence of a vector field is equal to the integral over the surface of the vector field dotted with the surface normal. So the volume integral of the divergence is equal to the surface integral of the vector field. Okay, so how does that help us? Well, we start with Gauss's law, which hopefully you remember from Physics 202, or we reviewed it a few classes ago. And that says that the flux of the electric field, the integral of the electric field, the surface integral of the electric field is equal to the enclosed charge over this constant epsilon naught. Okay, so that's our starting point. And then notice that for a given volume, the enclosed charge can just be written as the integral over the volume of the charge density times the volume element. So the charge is equal to the integral of the charge density over the volume element. So then just rewriting what we have up here as Gauss's law, we have the surface integral E dot dA is equal to the volume integral, substituting in for Q enclosed, the volume integral of rho dV over epsilon naught, or combining everything together, bringing epsilon naught inside, that would be the volume integral of rho over epsilon naught dV. All right, so now we bring in the divergence theorem, which says that the surface integral of the electric field is equal to, since the electric field is a vector, and this divergence theorem applies to any vector, the surface integral of the electric field is equal to the volume integral of the divergence of the electric field. Okay? So, but from what we've just seen, the surface integral of the electric field is also equal to the volume integral of rho over epsilon naught. So therefore we have the volume integral of the divergence of the electric field from the divergence theorem is equal to the volume integral, or both is equal to the flux, but the flux is also equal to, by Gauss's law, the volume integral of rho over epsilon naught. Okay, and the key idea is that this is true over an arbitrary volume. Okay, so this is true over an arbitrary volume of charge and an arbitrary distribution of charge. And the only way that that can be true is if the integrand, the divergence of E, is equal to the integrand, the rho over epsilon naught. So we find, so this is true over an arbitrary volume. This is an example of a volume over which it could be true. And so we find that the divergence of E is equal to rho over epsilon naught. And that is the differential form of Gauss's law. So this is the integral form of Gauss's law. this is the differential form of Gauss's law. The divergence of E is equal to rho over epsilon naught. And that's actually one of Maxwell's equations. Okay, what about finding the curl of E? Well, finding the curl, we're going to use, instead of using the divergence theorem, which has to do with divergences, we're going to use Stokes' theorem, which has to do with curls. And the curl of Stokes' theorem says that the surface integral of the curl of a vector is equal to the line integral of the vector over any closed path, okay, which bounds that surface, okay? So it's just a review. Okay, so let's see how we can apply this. If we take a charge, Q here, the electric field of that one charge is given by, well, you can probably remember KQ over R squared, R hat, but K can be written in a fancy way as 1 over 4 pi epsilon naught. And so we might ask ourselves the question, or there's no reason not to ask ourselves the question, what would be the line integral from point A to point B of that electric field? What would be the line integral of that electric field from point A to point B? Okay, and so we know how to do line integrals, and since this problem has spherical symmetry, we might as well use spherical coordinates. So the spherical coordinates, we've learned that the length element is dr r hat plus r d theta theta hat plus r sine theta d theta phi hat. And so therefore, E1, the electric field of the one charge, dot dl is just going to, since E1 only involves r hat, is only going to pick up the dr r hat part. So we just get 1 over 4 pi epsilon naught q over r squared dr. Okay, so that would be what we would be integrating over. And if we integrate from point A to point B, integrate that expression from point A to point B, that's the integral, a lot of constants, times the integral of A to B of 1 over r squared, which is minus 1 over r. So we get minus this over r evaluated from rb to ra, which can be rewritten as 1 over 4 pi epsilon naught times q over ra minus q over rb. Okay? All right, well, we don't seem to be too much closer to the curl of E yet, but we're getting there, I promise. So we can choose A and B to be the same point. Okay, right now they're different points, but we can choose them to be the same point, so that if A and B are the same point, A would, the path would curl back around and it would be a closed path, okay? And so over a closed path, the distance RA and RB would be equal, because it would be the same initial and final point, okay? So if RA is equal to RB, then we find that the line integral for the single charge is just going to be Q over RA minus Q over RB. Since RA is RB, that's going to be 0. And then since the electric field of many charges is made up of a superposition of the electric field of a single charge, a bunch of single charges, we can say that it must be true that the line integral of the general electric field should be equal to 0. Okay. And I should say at this point that this is true when charges are at rest. Okay, not when charges are moving. When charges are moving, we can get effects due to magnetic fields. But we're not worried about that yet. So next we use Stokes' theorem, and we say that we know that the line integral of the electric field is equal to the surface integral of the curl. So we have 0 is equal to the line integral of the electric field as the surface integral of the curl. But like in the argument for the divergence, if we're going around a closed loop, this surface that we pick that bounds the closed loop, the surface that we pick is an arbitrary surface, okay, an arbitrary surface. So the only way the integral of a vector field over an arbitrary surface can be 0 for all choices of surfaces is if the integrand is 0. And so we find that the curl of E should be equal to 0. Okay? And I want to say just again, this is true only when charges aren't moving. That is for electrostatic fields. If charges are moving, we can get magnetic fields and we can get electromagnetic induction, but that's for later in the course. Okay, the last thing I want to cover in this class is electric field, or in this lecture, is electric field by integration. This is something that you did in Physics 202, but it's something that's important to be able to do. And like we said before, the electric field is 1/4 pi epsilon naught times the charge over r squared. If we have a distribution, this dx shouldn't be here. It should just be dq. So we integrate up over all the charges in a distribution, q over r squared over 4 pi epsilon naught. Okay? So the problem we have is find the electric field, a distance z. Okay, so here's the distance z on this axis. This is the point P, a distance z away, above the midpoint of a straight line segment of length 2L. So this is the line segment of length 2L, the boldface right here, that carries a uniform charge per unit length, lambda. So there's charge per unit length on this is lambda. So if its length is 2L, the total charge on it would be lambda times 2L. Okay, so that's the total amount of charge in this length. And we want to find the electric field at this point, P, due to that. Okay, so we have to start setting up some geometry. From the origin here, our point is a distance z away, so it's equal to z times z hat. That's our vector from the origin to the point P. And then our vector we're going to be integrating over the line. And if we're at a position x is going to range from minus L to L as we go over the line. If we're at a position x, our line integral, our integral over the line is going to be the distance from that position x is just going to be x times x hat. Okay, the distance from the origin will be x times x hat. So that's where this point is. And then what we're really interested in is the distance from that little bit of charge that we're integrating over here to the point where we're trying to find the electric field. Okay. Yeah, we can say that dq, the little bit of charge, is equal to lambda times dx, the linear charge density times the length. So we have this vector r here is going to be equal to the difference between the distance from the origin to the point P minus the distance from the origin to this point. Okay, because this plus this is equal to this. So therefore, this is equal to this minus this. Okay, anyway, you can think about that and convince yourself it's true. And so we have script r, which we're calling this distance. Script r is equal to r minus r prime, which is equal to, as we said, z hat minus x hat. And this distance by the Pythagorean theorem is going to be z squared plus x squared square root. And we can define a unit vector along this length. R hat is equal to the script r hat is equal to script r over the length r. And then substitute in for our script r right here, and substitute in for our length of the diagonal square root of z squared plus x squared. Okay, so there we have the distance, sorry, the unit vector from where our charge is to where our electric field is being found. Okay, now we can apply this general formula up here for electric field. Forget the dx. We have 1 over 4 pi epsilon naught. We're integrating over dq, which would be, as I said, lambda dx. And we're integrating from minus L to L. And over the distance squared, which is the script r squared, so z squared plus x squared, times this unit vector r, which is, we just figured out, is this expression here. Z hat minus x hat over square root of x squared plus z squared plus x squared. Okay? So then evaluating this integral gets, we divide it up into two parts, a z hat part and an x hat part. And combining terms, we can pull out a lambda here. We can pull out a z in front of this integral over x, a z hat, and combine these two terms. So we're left with this integral over x, and then minus this integral over, minus x hat times this integral over x. Okay, so this is getting a little bit technical. The main importance is in setting up, starting with this basic expression for the electric field and setting up the problem like we've done here, but we're going to continue onward. So evaluating the integral, here it turns out that the integral of dx from, we're integrating this from minus L to L. So we get this as our integrand, and we're integrating this from minus L to L. So we get this as our result right here. Okay. And so, since x is, as we range from minus L to L, x is going to have an equal number of negative values on the left side as it does positive values on the right side. So therefore, as we do this integral, all these contributions are going to cancel. We're just going to be left with this integral over here. Okay? So we're left with, if we simplify this expression a little bit, bring the lambda in, and evaluate from L to minus L, and simplify this expression. I'm not going to go through all the steps. We get this final expression right here, which is 1 over 4 pi epsilon naught times 2 lambda L over square root of z times z squared plus L squared. Okay, so that's the expression for the electric field at a distance z above a straight line segment of length 2L. Oops, straight line segment of length 2L. Okay, so we can kind of check whether this makes some sense, some physical sense, because it doesn't look too, it's hard to tell whether this it's hard to verify this, whether this is correct. So notice if we're far from the line, if we're far from the x-axis, then the z coordinate is going to be much, much bigger than L. And if z is bigger than L, then we can neglect this L squared term here compared to z squared. And so we have just square root of z squared, which becomes z, times z, and we get 1 over 4 pi epsilon naught 2 lambda L over z squared z hat. Okay, but what did we say 2 lambda L was before? It's the total charge on the line segment, right? Because 2L is the length, and lambda is the charge per unit length. So what we've really got is 1 over 4 pi epsilon naught times Q total, okay, times Q total, where Q total is the total amount of charge on the line segment, divided by z squared. And that is what we would get, 1 over 4 pi epsilon naught Q total over z squared would be the electric field of a point charge at the origin if we were a long, long way away. Okay, so for a long, long way away, this line segment starts to just look like more and more like a point. Okay, so this limit here as z becomes much bigger than L, as z becomes much bigger than L, shows us that we have an expression which makes some sense. Okay, so this electric field by integration is something that you'll want to be able to do. It is a bit technical, a little hard to, but I hope I've described it clearly here. So in this lecture, we've done a couple of things with the electric field. We've shown its divergence using the divergence theorem. We've shown its curl using the not curling theorem, but the theorem involving curl, and we've done some electric field by integration. Okay, thanks for your attention.